Hello, we are the team formed by Maria Carlota, Anthony, Axel, and Victor from Matrix Modeling Group 301. In this activity, we analyzed the deterioration of a road section of several kilometers using a Markov chain model. The objective was to predict the future behavior of the pavement based on real data from the IRI. Why is a probabilistic model more appropriate in the analysis of the situation studied? Well, a probabilistic model is more appropriate because pavement deterioration doesn't occur deterministically. It's subject to multiple random factors such as weather, traffic, maintenance. Therefore, we use a Markov chain which allows us to model transitions between deterioration states with certain probabilities.
Why can this system be modeled as a Markov system? The system meets two key conditions of Markov process. The future state depends only on the current state, not on previous history. The transition probabilities between states remain stable over time. This allows us to represent state changes in a transition matrix. Ranges of numerical indicator about the deterioration of a road. The indicator used is the IRI. This measures pavement roughness, and it is classified as good under 1.8, acceptable from 1.8 to 2.5, poor over 1.8. Based on these ranges, we classified the sections and analyzed their progress.
Now, what methodology was followed to solve the problem? We were given data of the right, left, and the average of both roads, and we decided to make the analysis for both left and right roads separate. Using both sides separately increase the granularity of the analysis and ensure that the Markov model reflects a real behavior conditions. Averaging could artificially dilute the extreme values and making the model less responsive to the zones that are actually in poor condition. On the other hand, analyzing only one side will ignore critically the information of the other side. Well, for this, we first categorize the ERI data year by year and by kilometer. Then, for each kilometer, we calculate the average of the ERI and based on the values. We classify them with color: green for the good, yellow for the regular, and red for the bad ones. Later on, we counted how many transitions were from one color to another color for each year. Based on the results, we identified year-over-year transitions between the states and represent them in the probability transition matrix. To make these predictions for the following years, 2021 and 2025, we multiply the matrix for itself and use the result matrix as the new state for predicting the next year.
Application of the mathematical concepts and method used. We applied a first-order Markov chain defining states at road conditions and transition based on changes in IRI over time. We used cross-tabulation to count transitions between the states and normalization to convert counts into probabilities.
Now it is time to talk about the results that we got. At kilometer 267, the left road shows high persistence in poor conditions as more than 80% red roads stay red, with little chance of recovery. The right side shows slightly better outcomes, with a 35% chance of recovery. At kilometer 268, both sides have stable green conditions, but red roads, especially on the left, are almost fully deteriorated, with 92.9% persistence. At kilometer 269, green roads degrade quickly. Less than 20% on both sides stay green. The left road sees 50% red persistence with some recovery. The right shows similar patterns. Finally, at kilometer 270, green to yellow transition is minimal, and yellow is highly persistent on both sides up to 96%. So what are the most important results? Well, green state tends to persist with 70 to 90% depending on the location. Yellow state has strong persistence from 85 to 96%, but also transits to red in degraded segments. Red state often absorbs, showing no natural recovery without maintenance. We realized that in kilometer 267, the degradation occurs faster, while from kilometer 268 to 270, there's a slower degradation and a greater state persistence. This analysis is endorsed by the predictions for future years. Once the green roads start deteriorating, the probability of transit to red state increases, while the green-yellow roads vary over time. From 2021 to 2025, the percentage of roads in red state increases in all roads.
We are going to explain the relationship between the data obtained and the data used, and how they were handled in the mathematical models, and their relationship between the situation under analysis. The relationship between the obtained data and the data that we use lies in how we build and interpret the transition matrices. This was by making condition vectors year by year, and later on create matrices that show how the pavement change over the time, whether it stayed good condition, worsened, or improved. These transitions were made modeled by using Markov chains, where each matrix value represents the probability of moving from one condition to another, based on the real-world observations.
Markov chains provide a realistic and statistically grounded model to predict road condition transitions. Most segments are stable, with minimal degradation except for kilometer 267, which shows significant deterioration. The transition matrices gives insight into where preventive maintenance should be prioritized. Some general conclusions regarding the solved problem situation are that the model accurately reflects probabilistic degradation of the road surface. Markov chains are appropriately due to the memoryless nature and the ability to track gradual conditions and changes over time. Transition matrices help to prioritize road maintenance by identifying segments with high probability of deterioration, and future work can include predicting multi-year state evolutions and incorporating cost-benefit analysis for the repairs. This is the link to our Excel file, and thank you very much for your attention.